We typically use coordinate systems to analyze physical phenomena. Our coordinate system has the origin 0, 0. Let's add a point A. To get to A, we move 3 squares in the x direction and 3 squares in the y direction. We can assign point A the coordinate 3, 3. Now let's add point B at -4, 3. These coordinates hold true for our system, but as soon as we shift that system, maybe by rotating it and shifting the origin, we have a new point which is the origin of our coordinate system, and A is no longer at 3, 3. Let's take a look at what traveling through the system looks like. Say Sticky the stick figure lives in a house at point B and wants to visit their friend at point A. Sticky travels 7 squares in the x direction to get there, right? Well, technically the Earth orbits the Sun at 30,000 meters per second, and the solar system orbits the Milky Way at 828 million meters per second. So does Sticky really only travel 7 squares? Let's visualize this. We have the Earth and the Sun. Point A and point B are both on the Earth's surface and travel around the Sun with the Earth. If we add our coordinate system to this model, we see that it's also traveling around the Sun. If we want point A and point B to remain fixed. So just like the Earth, we can set our coordinate system to rotate around the Sun. And in the exact same way, we can say that the coordinate system is orbiting the center of the Milky Way. So yes, Sticky did travel 7 squares within the coordinate system, also known as the frame of reference. Pause. Let's recap what this all means. Reference frames or coordinate systems tell us where an event occurs. For example, an event could be the arrival at house B. In addition, reference frames can shift with a constant velocity, which means no acceleration. Think the Earth orbiting the Sun. This brings us to the concept of space-time. First, we have space, our coordinate system with 3 dimensions. Second, time, one more additional dimension to help us understand when and where events occur. Add these together and we have space-time. Using a clock, the reference frame can measure time, and an event is an occurrence that can be assigned a single point in space-time. Let's visualize this to help you get a better understanding. Let's say we have a frame of reference with the dimensions x, which is our space coordinate, and t, which is our time coordinate. Point A is at the origin, and point B is 7 squares away from A in the x direction. At t0, A and B both lie on the x-axis, but let's say t equals 3. Points A and B move through space-time 3 units in the time dimension, so even if both points don't seem to move through space, they are still traveling through time, just like you and I are right now. Let's say Sticky realizes they can't visit their friend at point A because we are in the midst of a global pandemic and walks back to their home at B. We can draw this as an arrow going from point A at t0 to point B at t equals 3. The event of leaving occurred at the space-time coordinates 0, 0, and the arrival back at home occurred at 7, 3. Simple enough, right? Nope. The premise of relativity theory is taking events that happened in one reference frame at a specific space-time coordinate and seeing how they carry over to a second reference frame. These are called transformations, and 3 minutes is not nearly enough time to cover them.